So this question, your concern was with the things being at an angle and how to solve then when I have tension at an angle and the incline. Is that correct?
Yeah.
Okay. So are you starting with a free body diagram?
Yeah.
Okay. So let's just kind of remind ourselves that the force of gravity comes straight down. I like to draw it to the bottom of the whatever surface I'm working with. And then my force normal is always up perpendicular to that surface. And these are exaggerated, they're not drawn to scale. And then this one is easy because it's just coming straight off of it. So it's parallel to the surface that it's on. So that's my force of tension. And then the other one that is right on the surface is the force of friction. So if this thing is going to go, what we're looking for is for the friction to oppose the motion that would make it go up and down the hill. And the fun part about this is I look at this is 22, this is 34, so we're not entirely sure what direction that force of friction is. And we're going to see how to determine that if my initial guess is right, that the friction opposing the motion going up the hill with the tension, or is the friction opposing the motion of the force of gravity pulling it down? That we don't know yet, but we can just kind of make a guess. And then here, are you good with that?
Yeah.
Okay. Then here I have the force of gravity from this one, and I'm just going to call this, okay, so force of gravity B, force of gravity A, just so we keep those straight. And then the force of tension up. So there's a couple things we can ask ourselves to get this going. And the first one is, how do these tensions relate to each other? Are they the same or are they different? What do you think?
Well, with this, I know we were just talking about having equal and opposite.
Okay.
Would that apply in this case?
Absolutely, absolutely. So this line is connecting between the two. And one of the things that you always see is that we'll say that this is a massless pulley and the line is like this perfect line. So it's massless. So it doesn't end up participating in anything other than being tension. So connected between these two things, that tension is completely the same. The tension feeling that's felt here is the same as the tension felt here. So yep, it is the same. So yes on that. If they accelerated, so if they did, would that be the same?
With the different weights, does that affect the acceleration?
So the different weights affect the acceleration as far as the magnitude goes, but that wouldn't affect the acceleration as far as, is it the same or is it different?
Okay, so then it would be the same?
Yes, good. So yes, if there were acceleration. Now this question was saying to keep it at rest. So we're not going to have any acceleration, but if we know these two things, this part actually becomes a system. So let's see if we can't figure out how to do it as a system when we're all done. But now I've answered two things. I can relate these tensions to each other, and I know that acceleration would be the same if there was acceleration. So I have a couple of pieces that I can relate to each other. Now I'm at an angle. So the thing I like to do is draw a line, just a little dotted line, to remind myself that this angle here is the same as that 19. So the angle between the gravity, and if you extend this line down from the normal, between gravity and the normal is going to be the exact same as the incline. So now let's do let's do a free body diagram. Let's start with that little dot I made there. See, so I like to do my normal first, just to kind of make my axes there. And the force of friction is always going to be perpendicular to the force normal. So if you think about that, the force normal is like pushing on a surface or the surface pushing back on my hand. Well, the force of friction is that experience between my hand and that surface, or the box and that surface. So the force of friction is going to be on the x-axis. when I rotate it like this. Then I look at it, and the force of tension is also parallel to that surface, so it's coming out this way. So far, what's nice is 3 of my forces are on the axes. So I only have one more to do, and that will be the force of gravity. Let's just draw a little line down here. And the force of gravity is coming out to the left of the normal. So make sure I draw it out here. And this is for mass A. So I do know, and I can remind myself that I know that this angle here is then that 19 degrees. And now we come over here, and I look at this, and like this is the nice one for doing any math with, because for mass B, all I have is gravity and tension. So I'll have the force of gravity down and the force of tension up. So let's label that A. Tension is the same for both. So now before I can do any kind of summation of forces, I need to make sure I define which way is positive. And for this one, I have like an equal number of things up and to the right and down. So I'm just going to go with the standard up and to the right is positive. So I can come over here, and this is going to have just one sum, just in the y. And I've defined up as positive, so I have this force of tension minus the force of gravity. I don't know what that sound is from the kitchen. Hopefully it's not falling apart. And this thing, we want it to stay at rest. So what is that going to equal?
That equals 0.
Perfect. You got it. Awesome. So what is one of the things I can do immediately with this? I can say, okay, so the force of tension is going to then equal mass B times the acceleration due to gravity. And I do that one because I look over here, and if I need to solve for something, I know now I can replace this with a known quantity. I know that. This one, because I have friction and tension, well, the friction piece tells me that I have to know what's going on here. And the one thing I like to do is point out to everybody that when I look at this drawing here, for gravity, what I'm looking at is I have, the normal is my y-axis, here's my y component of gravity, ideally a straight line down from the normal. My x component of gravity is the thing that would accelerate it going down the hill. So you see my x-axis is parallel to the surface itself. So this is the thing that makes it go. This is the piece that keeps it on the surface. So when I do my sum, as far as breaking it into its angles, I know this angle, well, let's start with our x's so we can do that right now. So what I just drew down here is the y component of gravity, and there is my x component of gravity. So for my sum, if I go in the x, this is the x, and it's going in this direction, so it's opposite side. It's going away from that positive sign, so it's negative. So my piece there is negative, so I'm going to just start with my force of tension so I have a positive piece, just because I don't like starting with negatives. So minus, now let's look at this. What trig function would I use here?
It's opposite.
Perfect.
So you would use sine.
Perfect, yeah. So FG sine theta. It's the only thing at an angle, so I'm not going to worry about naming what that angle is other than theta. Let's see, so I'm in the x, I've taken the x component there. The only other thing I have here is minus the force of friction. And so what does that sum equal, 0 or MA?
Would that be MA?
Careful, what's the question that we're looking for?
Oh, if it's at rest.
There you go, yep. So 0. And then let's do the y. And the reason I know I need the y is I have this thing, force of friction. So I can remind myself a couple of the definitions that we have. You know, the force of gravity is mg, and that to just stay at rest, so it's just not going to move, that split second before it starts sliding, force of friction does equal the force normal times mu. If it is moving or just getting ready to move, so it's like that maximum amount before it would start sliding, then this is true. Are you good with that?
Yeah.
Okay. So then in the y, let's see, start with my positive one. I have force normal. These two are both all in the x, so I just need the y component of gravity. So minus fg, and what is that angle here? Is it cosine or sine?
Cosine?
Perfect, cosine of theta. And that equals,
Would that also equal 0?
yep. So in my y, the question I always ask myself, am I flying up in the air or am I in free fall? If the answer to those is I'm not, then the sum of in the y is 0. The
Okay.
motion, I'm sorry?
Oh, okay, that makes sense.
Okay. And then the motion piece, you're looking for the component that is parallel to the surface that we're moving. Well, that's the x piece. So if it were going to accelerate, it's going to be the x piece that's going to do that. So I look at this. This is nice because I need this force normal times mu to get to my mu. And this is just the two pieces. So I can rewrite this in terms of mass A. You know, force of normal, moving this over to this side of the equation, I get, let's see, mass A times gravity times cosine of theta, which is nice because these are all known quantities. So I have a known quantity here, a known quantity here. Force of tension, well, that's what will go here. This, well, that's just the mass of A times gravity times sine of theta. And the force of friction, well, that's going to be equal to force normal times mu, which we just figured out is mass A times gravity times cosine of theta, all of that times mu. So then we're almost there, because now I can just put in the pieces that I know. Most of that in the screen. So I've defined force tension as mass B times gravity. Fg, this is for this mass A. So Fg then is going to be mass A times gravity times sine theta. And the force of friction, we just figured that one out, is mass A times gravity times cosine theta times mu. And so the equation that we wanted is that the force of tension minus the Fg sine theta minus the force of friction equals 0. That's where we wanted all the substitutions from. So force of friction, the question was, remember, asking for mu. Force of friction has that coefficient of friction in it. So if I want to solve for this, then the force of friction is the one I'm going to move to the other side. So I'll have, making my substitutions now, let me do it in a different color. Force of tension is mass B times gravity minus mass A, oops, A, not G, A, G, oh, that's horrible when I keep making my A's look like G's, sine theta, it's my Fg sine theta. And let's see, minus or equals the force of friction. And the force of friction we've defined as mass A G cosine theta times mu. So in the end, now I can isolate for mu, I get mass B times gravity minus mass A times gravity times sine theta divided by that piece. mass A g cosine theta equals mu. So one of the things that I said, we can look at this in terms of our forces as a unit, as a system, is notice that tension is gone from here. Okay, there's my masses. So no, I'm not going to do that. That'll get more confusing. But you can see that this thing, well, now let's put in our numbers. I'm sorry. I'm doing like too many things in my head simultaneously. Because the one question I said is this correct? Is this friction in the correct direction? So is friction opposing the motion going this way, which is what the assumption I made was? Or is friction going uphill opposing the motion coming down? If this is negative, then the direction that I chose is incorrect. So now I can put in my values. I have, let's see, 22 kilograms times 9.8 meters per second squared minus mass A 34 kilograms times 9.8 times sine of 19 divided by the mass A is 34 times 9.8 times cosine of 19. There we go. Let me just put that in a calculator. I don't think I'm in radians. Let's see. Yep. So what did we get? Is this positive or negative?
Would it be positive?
Yep. Cosine of 19. And I get 0.34. So it's positive. That means that the force of friction is indeed opposing this motion. Instead of it sliding down the hill, it's keeping it from going over. Does that make sense?
Yeah.
Cool. Does the process make sense as far as what you were asking?
Yeah, I think normally I get a bit confused with just the substitution. I kind of sometimes get turned around there, but that definitely makes sense now that I see it worked out.
What I would say, if that's where you're getting lost, and it's really easy when you're first starting dealing with everything in terms of letters instead of just numbers, is that as you can see when I started getting down here, if I make this kind of memory trick, a reminder for myself of these things that I know for how they're defined, then as I get to things, especially with just two terms, go ahead and immediately solve for them like I did here. So I know, okay, I have the force normal in terms of known values, and I know that the force of friction is applicable. So this is the force normal times mu for this. So now I can solve for that. And then I ask myself, well, the only thing I want to know is what is the force of friction? Well, can I get there from here? I'm like, so the force of friction equals this. Well, without mu, so I would have to know what this is. So that means that I have to solve for something. When I come up here, I'm like, okay, so force of tension I can get from this one. So then that keys me in that I can use this equation to solve to get to that coefficient.
Okay.
Does that help?
Yeah.
You sure?
Yeah.
Okay.